All right, thank you for the introduction and thanks for having me today. Let's see here. Okay, so I'm going to be talking about kind of picking up from some of the things that Carla did a really fantastic job of introducing, kind of starting to move more into biological systems and how PFASs interact with living things. And I'm going to start kind of by just highlighting a major problem, which is that the vast majority of studies, especially related to PFAS exposure and effects, focus on a few well-studied compounds, right? PFOA, PFAS. And we know now that there are thousands or maybe millions, depending on how you define them, of PFASs. So this is some examples from the PubChem Lite database of just all of these different funky structures. And we really don't know a lot about exposure, bioaccumulation, toxicokinetics, toxicity of any of these other compounds. And kind of underlining that further, we know that there's a lot of unknowns. So PFAS dark matter, or this unknown total organic fluorine that's in human serums. This is two examples of studies, one from China and one from Sweden, where in the general population we can explain sometimes only about half of the total organic fluorine in people's blood. So there's something to the story that we still need to uncover. So in my group, we use analytical chemistry as kind of a flashlight in the dark to try and illuminate some of these novel compounds and understand how they interact with our bodies better. So the tools we use high-res mass spectrometry, and we do targeted analysis. We look at things like biomonitoring, PFASs, and serum. So we look at about 50 PFASs for targeted analysis. This is just showing the kind of performance of our serum methods for recovery, and our detection limits generally below 0.1 nanograms per mil, which is where you want to be for looking at human blood. But we also do suspect screening and non-target analysis. So on top of that targeted quantitation, we can also screen for known or theoretical PFASs within whatever mass range we're using, usually 100 to 1200 Daltons. And we can match based on exact mass as well as isotope pattern. And then in some cases, if we have fragmentation data, we can also get a higher confidence identification based on fragmentation fingerprints for the structures of these molecules. So we've been applying these techniques to look at different, biological samples. And we do a lot of work in serum. So one of the first kind of lessons that we've learned that I wanted to highlight is really that PFASs are everywhere, and these fingerprints are in our serum everywhere. So you can see kind of these distinct different fingerprints of PFASs, depending on things like the species you're looking at, and also the kind of main sources of PFASs to that species. So here we're looking at a fingerprint for a first responder from the World Trade Center health program here at Stony Brook. Pretty high levels in serum, and also you can see a pretty high branched representation, as well as linear PFAS, and some of these other short chain compounds are mostly what we see. And then comparing that to a very different kind of scenario. This is a white shark from off the coast of Nova Scotia. So we see these things everywhere. Lower levels in the serum, and also you can see really high representation of these really long chain carboxylic acids, which we see a lot associated with fish, bioaccumulation in fish. And even among humans. So if we look at two fingerprints from different groups of humans, so now we're comparing our first responders to avid seafood consumers here on Long Island. And you can see the difference in the fingerprints here, where again, those long chain carboxylates are a bit more accentuated in the seafood consumers, and the branch signature is a bit different. So the take home here is that PFASs looking at these fingerprints can help us get an idea of, what are the sources of exposure, what might be the implications of this exposure. But if we could add in more novel PFASs, some of these novel structures, it would give us more of a clue about source identification and, what kind of the more holistic understanding is of the entire exposure that's happening here. But it's really hard to look for novel PFASs. So the fingerprints I'm showing you right here are mostly perfluoroalkyl acids that are in our targeted lists. And the reason that it's so hard in these kinds of samples is because they're present at really low concentrations and they're very difficult to find in a biological matrix if you don't know what you're looking for. So we use these high-res mass spec tools to do what I call a biological prioritization of novel and unknown PFASs. So we're taking commercial PFAS mixtures and subjecting them to different kinds of tests in the laboratory using things like in vitro metabolism assays, as well as in vivo dosing studies with an entire complex mixture in order to identify biological transformation products that form when we're exposed to PFASs, as well as novel, highly bioaccumulative compounds. So kind of prioritizing what's actually accumulating in the body that maybe we weren't monitoring for before. And by doing this, we can inform our analysis. So we can build high-res mass spec libraries of these novel compounds that are bioaccumulative. And then we can use those libraries to start looking, kind of give us an idea of what to look for in our serum samples. And we've used these kinds of workflows to find things like unsaturated versions of PFAS at low levels in human serum. We're seeing those pretty widespread, these structures in first responders, as well as some communities with highly contaminated drinking water. So these aqueous film-forming foams, Carla touched on, are highly complex mixtures containing hundreds of different PFASs, and they're very highly relevant for drinking water contamination, as well as different exposure scenarios among first responders. So I'm not going to get into the chemistry here too much, except for to say that one of the first things we need to do when we're doing these kinds of studies is really understand the composition of the mixture as well as we possibly can using these high-res techniques. So both doing high-res mass spectrometry, which is what I'm showing here, and then we also use the top assay to look at things like how many precursors are present in this mixture. So here, this is a historical AFFF foam that we've been using in a lot of our studies. You can see looks like it has quite high contributions from short chain PFASs precursors. So we're getting a lot of formation of the C3 through C5 carboxylates. So good information to have when you start doing these kinds of exposure studies. So when we dose a mouse model with this AFFF for 10 days and then do a 6-day deparation and collect serum and urine, this is what we see for the serum. So what we're doing here is looking at the serum to kind of look at what pops out as being bioaccumulative that isn't in our biomonitoring lists. And we found a number of novel substituted perfluoroalkyl acids. We have cyclic unsaturated, hydrogen substituted, oxygen substituted, a number of different kind of diverse structures that are bioaccumulative. We can also look at what's excreted, which can be important for things like biomonitoring in impacted communities when the exposure is still ongoing. So we collected urine from these mice throughout this dosing study and then conducted an iterative QTOF method to look for different kinds of conjugated metabolites. And we found a number of glucuronidated perfluoroalkyl sulfonamides. So these are precursors that are being conjugated and then excreted through the urine during exposure. We've got pretty high confidence in these identifications. And looking at the peak areas, it looks like this is a pretty major excretion route, at least during a high dosage exposure like this. We can also look at what's transformed, so biological transformation. We know, PFASs, perfluoroalkyl acids, are extremely persistent, right? But there are a lot of other compounds in that AFFF that are actually metabolically labile. So looking at this kind of bioaccumulation chart here, you can see I'm going from short chain to long chain. And usually what you would expect is for the longer chains to be more enriched in serum as opposed to the short chains. But we see these kind of interesting perturbations, which are likely showing us that these are products of precursor biological transformation happening in this mouse model. So it looks like there's a lot of formation of the C6, the C7, as well as potentially some of the branched PFAS. So now we've been working on kind of trying to chase this down using in vitro methods. And this is kind of at its early stages right now, but we're using liver S9 assays with the same strain of mouse. And we're trying to do both positive controls using things like ethyl fossa. And when we do that, what we're finding is that there's dealkylation, and our major product is the sulfonamide, not the sulfonate. So in a mouse model, in a living thing, we're seeing formation of these sulfonates, these perfluoroalkyl acids. And when we look at it in an in vitro system, we're seeing the sulfonamide. So we're not really seeing agreement between our in vitro and in vivo systems. So these are kind of the major products that we're seeing in our positive controls, and then in our atypical lactose system, we're seeing sulfonylaminoacetic acids as our major product. So really not agreeing with the in vivo, but the chain lengths agree. So we're seeing formation of C6s and C7s, just not to the same extent. There's some other processes happening in the body that we are not recapitulating with these in vitro systems. So conclusions, I'm hoping that I at least have convinced you that through this work so far, we really need to test exposure relevant mixtures, not just one compound at a time that we can get a neat standard for. We don't have standards for a lot of these compounds, so we need to go to the mixtures themselves and look at those. We also need to develop more MSMS libraries to kind of identify these biologically relevant PFASs and their PFAS transformation products. So what we're trying to do is really use these in vivo models as well as in vitro models to inform our biomonitoring and make it better. So thank you for listening, and I would like to thank all of my collaborators as well as my funding sources and all of my excellent students pictured here. I think they're all here in the audience. You can talk to them later. This is all their work. And thank you. Happy to take questions after.